Good morning. I need first to ask if you are hearing me. If you are not hearing me, please send me a quick message. You remember that we had these problems last Wednesday, so let's hope that this morning is going to work better. Anyway, we were discussing last Wednesday about our problem, the problem from which we started, uh, which in simple words would like to ask whether it's better to substitute the conventional plastics which are obtained from oil with the so-called bioplastics, which instead are obtained from agricultural products, in practice derivatives of sugars, mainly cornstarch or other kinds of starch like potato starch, or there are other possibilities, the possibility to get biodegradable plastics from oil-based products, like it is the case for polycaprolactam. In that case, you have biodegradable plastics at the end of their life, so you improve the end of life. With respect to other scenarios, we call scenarios what happens at some time, in particular at end of life. And of course, it's always a question of alternatives. So we have these different kinds of plastics, and we can have also another possibility, which is bio-based plastics. So getting the conventional plastics, the ones we know very well, like polyethylene, polypropylene, polyethylene terephthalate, even polystyrene, from something which is of biological origin, which might be, for example, kinds of vegetable oils for some cases. In other cases, for example, ethanol. From ethanol, you are able to get ethylene and the derivative like polyethylene terephthalate. Okay, you find all that in the two previous files. I have to remember that the files are in the web page, on my web page on the website. If someone is not finding them, I'll send them the link. And I'll put the lectures. Let's see if I am able to put on the e-learning platform. Otherwise, I will put them on the YouTube and I'll let you know. I have a YouTube channel with my name. Okay. For any questions, please send me an email. Where are we today? We would like to compare these two possibilities, so the traditional plastics and the new so-called new bioplastics. Bioplastics is a confusing term because it gives you the idea that it's necessarily better to produce something because it's bio. And we will see also other terms of confusion, other possible confusions later on. But anyway, what we need to concentrate on is that you may remember that if you want to evaluate the environmental sustainability, you need to have some factors. So you divide that main or even philosophical question of environmental impact into a number of items on which you are able to take some measurements Without numbers, we are not able to say anything. Even with numbers, we may have difficulties because you need to be sure that numbers have been acquired in repeatable ways, and there is also a local aspect. Because, for example, you produce energies in different ways in different countries with different combustibles and so on. And so this may produce different effects. Today we try to concentrate on the greenhouse effect. The greenhouse effect means that basically you get atmosphere like it was in a greenhouse. So basically you get global warming, and there are some gases, greenhouse gases, so GHG as an abbreviation. Greenhouse gases produce that effect. The emission of these gases produce that effect. There are a number of activities, not only human activities, but also activities connected with agriculture, which are still human, but involve the contribution of animals that produce these gases. And even, of course, breathing, respiration produces, for example, carbon dioxide, transform oxygen into carbon dioxide. In contrast, photosynthesis transforms carbon dioxide into oxygen, so gives a negative contribution to the environmental impact. In other senses, it is positive for us. It reduces the environmental impact. So greenhouse gases are a number of different gases. We mainly concentrate on carbon dioxide, and the measurements are made on carbon dioxide. In practical terms, all the other gases have an impact which is compared with what is produced by carbon dioxide. So we measure greenhouse effect in carbon dioxide equivalents. Here you see to the left the whole cycle, and this is quite obvious because in practice you have some, you know that atmosphere is composed by mainly by nitrogen and oxygen. There is a very little amount of other gases, including carbon dioxide, which needs to stay at an amount of around 300 parts per million. Instead, it tends to grow, and even a growth of a few parts per million, together with the contribution of other oxides like nitrogen oxides, or like ozone and so on, may increase that greenhouse effect and that global warming. What we can say is that we have different scenarios. We have composting. Composting means biodegradation at a high velocity, at a velocity compatible with agricultural use. So, as a matter of fact, you need the material to be gone, to have disappeared, and to be ready to be inserted into compost, into what has been produced by human activity, basically. So animal dung, and you can insert compost into compost the residues of also bioplastics, provided that they are compostable, which, as I was saying last time, compostable means more than biodegradable. You might be biodegradable as a material, but not at a velocity which is of interest for agriculture, too slow. Composting has precise requirements which we'll give later on, and they are important because some materials, some bioplastics, are certified as compostable. So we certify they are going to work in compost. Of course, there are other scenarios. In plastics, there is always the tricky question, the long time question, whether we are able to incinerate plastics. Some plastics, we are not able to incinerate them. For example, the ones that produce chlorine, they create some effluents, some gases and vapors which go out as dioxins and furans in some cases, and which means in the end that we are not able to incinerate them. Incineration is one of the ways of burning materials at end of life, and that means that we really don't control too much the amount of air which is introduced. It's a kind of natural flow of air. Then we could have pyrolysis when we control better air, the amount of air, and gasification when we have mainly oxygen. We tend not to have nitrogen. We tend to have an oxygen flow in order to produce some chemicals, some very well targeted chemicals. Okay, there are other options, of course. The usual option, the option which is used a lot still in many countries, is landfilling. We want to avoid landfilling of plastics. In principle, you'll see today that not everyone agrees with that perspective because it's difficult. You understand that landfilling is the easiest option. We can landfill, and provided they are not toxic or not noxious for anyone, we could landfill materials. The problem is that we are in this way using land, which could be destined to other destination, could be another one, a more rentable one, also a more productive one, or you could recycle plastics. Okay, recycled plastics needs a lot of discussion as well, because we have, as I was saying, we have three types of recycling. We have mechanical recycling, which is the one which is always present when you talk about recycling, not reusing, recycling, when you transform, therefore, the geometry of your material at end of life, you always chop or grind it. So there is always mechanical recycling. Then you have thermal recycling, which means that you melt it, provided it melts, and not every material melts, not every plastic melts. Then you have chemical recycling, if you push to the extreme the thermal recycling and you want to depolymerize and obtain the original, for example, hydrocarbons. Okay, you can see at the bottom right and the top right as well, the top right in particular, you can see that there are sinks. Sinks mean something which we don't know exactly. There is a precise definition at bottom left, but apart from the precise definition, what sink implies is that we have something that we produce and has no use, in principle, but we need to find use for sinks. For example, carbon is stored in the soil or in landfill and so on. We could make a use of that carbon because, for example, it could improve some kind of activity, even agricultural activity. We could reduce, as I was saying, here you can see sinks, beneficial use and solutions. So sink has no use in principle. We want to find a use. Possibly we could use less fertilizer because we have a carbon storage. Or we could generate energy. From incineration, we tend to generate energy. And therefore, We don't use the fossil fuel. We don't need combustion with fossil fuel, which is good in principle. Of course, there are problems because there are filters and incineration produces. Please remember that incineration produces ashes. The bottom line, you will find ashes. Ashes may contain a number of products which might be even toxic or unhealthy. In any case, it may contain some metals, even heavy metals, etc. Landfilling has the problem of land use. We want to avoid landfilling under the soil into water. You have the aquifers down the soil, and what is produced by landfilling could leach into these waters. Then we have recycling, and recycling means that we could possibly recover materials from recycling. Recycling of some materials are very effective. Recycling of glass recycling is very effective for one precise reason, that glass is constituted by a main material, which is silicon dioxide, silica, and silica is of large use, and also it's easy to separate from other metal oxides which are present in glass, for example, to give it the characteristic colors it's needed in some cases. But it's easy to separate anyway silica from these metal oxides, and so glass is very good to recycle. Also, we need therefore to investigate this kind of scenarios and the way we want to. Okay, plastics. Let's concentrate on which kind of plastic we want to replace. Which kind of plastics are really recycled. It is important that we have a classification of plastics according to recycling, which gives numbers. You give number to the plastics, number from 1 to 7. Basically, 1 to 6 represent a single plastics. Here, for better clarity, you see some uses. Uses are countless, but you see some important uses of any of these. We will have the polyethylene terephthalate. We have the high-density polyethylene, which is number 2, and then the low-density polyethylene is number 4. Number 3 is polyvinyl chloride, which you may remember produces the problem, for example, in food. You can see that food packaging in polyvinyl chloride is no longer allowed. And you may find also in films which wrap your food. For example, this is very typical for cheese, for pizzas you buy in the supermarket and so on. You may find that they don't include any PVC. So number 3, there is no number 3, because number 3 may leach some chlorine into the food, which is unhealthy, and it has consequences also in terms of recycling, of incineration. It might be recycled. Although you may see that some uses are quite niche uses, so they are not mainstream uses. So it depends on the amount you have of this kind of use. But anyway, PVC is very diffused still. And then we have number 5, which is polypropylene, and number 6, which is polystyrene. Polystyrene starts to be quite tricky. It's a kind of glassy plastic, and in some cases it's so light, low weight, and which means that you have a high volume and low weight, which means in practice there are problems in transportation. It's not cost effective in some cases to recycle, because cheap large volume, low weight. That means that you make little more in recycling. So the best one to recycle, if I would say as a kind of initial consideration, then of course we can go on and on. One, because one is mainly bottles, and then 2 and 4, also, and 5. Also 3 and 6, but with some caveats, as I was saying. Okay, number 7. Number 7 is all the rest. Number 7 means that all the rest is number 7, which means in principle that we are not able to recycle that much, number 7, because there is a mix match of a number of plastics. Mix match, which in another sense means that we need to separate all that. When you got at the collection system, you have number 7, and you need to separate, or you need to make a kind of mechanical recycling of very low value. You may have a mix match of plastic which you just grind and put in other new plastics for some reasons, color, providing some elongations like better mechanical properties. Well, but it's a low use, a low quality use. So, okay, we want to replace 1, 2, 4, and 5, but mainly 1 and 4, I would say, also 5 possibly, with bioplastics. Let's see what if this is worthy to do. There is not a simple question, it's not yes or no. It's important to see the whole of the problem. This is the engineering classification of plastic, thermal classification of plastic. Some of these you don't care that much because they are niche, some plastic which are used for some particular uses. Anyway, this is the maximum use temperature. Please note that the maximum use temperature is not the processing temperature. In other words, if I want to melt this plastic, they don't melt at that temperature I'm showing here, but they melt at higher temperature. But I am able to use these plastics at these temperatures. You may see that the two ones that we know quite well, polypropylene and polyethylene, are below 100 degrees. Please consider that the bottom line can be considered around 50 degrees. So in practice, there are some cases, there are some plastics which are unsuitable when you are in the kitchen. There are some plastics which are unsuitable to be put into the oven. For example, you could not put polypropylene, a polypropylene tray into the oven because it will melt. Well, it will not melt, it will soften. It will melt completely. Polypropylene melts completely at 170, 180 degrees, but it starts becoming softer and unsuitable and, well, taking strange shapes and so on at 70, 80 degrees. So you cannot put it into the oven. That's also why we can think of replacing these with polylactic acid, which is the most popular bioplastic at the moment. Polylactic acid shows some problem below 100 degrees, at 70, 80 degrees, because starch gelatinizes, means it becomes a kind of jelly stuff. But it is not a big problem, because also polypropylene and polyethylene have the same problems. They start to soften, and whilst PLA gelatinizes, but that's about the same thing. Okay, you have other plastic. You have well, there is a word in here. Well, I'm just saying some few things. For example, you can see the PTFE, the so-called Teflon, which is above 150 degrees and which is used at high temperatures, very performing and so on. And I don't go into details of all the plastics. We can see, though, at the center of the triangle, PET, and PET, it's the polyethylene terephthalate, which is much more performing than polypropylene and polyethylene. In fact, in terms of temperature. Okay, so this is the idea. This gives you an idea of what exists in terms of plastics. If you are curious, you may find the other what the acronyms mean. For example, we have polyamide, which is nylon. Again, at the center of the triangle, there are different kinds of polyamide. Polyamide 1,1, 1,2, 6,6, and so on. The polyamides are very diffused as well. They are very good for tensile properties and so on. You can see from this picture, I'm showing this picture, which is impressive because you may imagine that we are not able to substitute all these materials with bioplastics. Just few of them possibly. There are some which is really difficult to substitute, like polymethyl methacrylate, which is close to polypropylene, which is the so-called plexiglass, and it's really very difficult to substitute. Plexiglass is the name of the patent rather than materials. Okay, let's go further. What I was saying is that talking about sustainability, we have environmental sustainability and we have social and economical sustainability, which are connected. We concentrate on environmental sustainability, but we cannot get rid of the other aspects. For example, it might not be bad for the environment, but it might be bad for human health, which is not exactly saying the environment, but it's not exactly the same thing, but it always involves sustainability in a wider sense. So I'm showing these plastics, some of these plastics, and I'm showing some of these food system stages. The food system stages. Here we are not talking of bioplastic yet, but there is still agricultural production, processing and storage and so on. Why there is agricultural production? Because we concentrate on food packaging. And agricultural production, it's the bulk of food system stages. We could use in this is for food packaging basically. And in practical terms, most packaging is food packaging. In terms also not only of production, I'm not sure about the right amount of production, so I may not say that food packaging is the largest amount of packaging which is produced, but in terms of visibility is for sure the most important one. Also because it requires a certification which goes well beyond what is required for the other types of packaging. Other types of packaging may require some indication, for example, on the bacterial content, but this is very general, that they don't get dirty and so on. You may see that food packaging is completely different. The level of certification required is completely different. I'm not going to read and to go in details about all this, but it is important that it guarantees that packaging guarantees food access and food utilization and stability. And therefore it doesn't ruin, it doesn't spoil food before time. It needs to ensure that food packaging needs to ensure the food goes until the expiry date without giving problems, without giving raise to complaints and so on, because the food is becoming moldy before the expiry date and so on. And plastics work reasonably well on that, reasonably well, with some limitations, but it is, for example, it is reasonably good. For example, as I was saying, PVC cannot have direct contact with food because of some problems, but there is also some kind of PVC which forms packaging which is not in direct contact with food, but it belongs to the food productive system. Okay, so there are a number of questions. One of the main questions about food packaging, you can read, and please read all of this, because especially to start thinking about what is the impact. It's more important than learning by heart what you are looking at. It's important that you think what all this implies. There is a big question about this, which is microplastics. That's one of the reasons why we are not enthusiastic about land filling. Well, there is land use, there is leaching into aquifers, but there is also presence of microplastics, which can go at very large distances, can even go into the water system, seawater system, and pollute the sea and so on. Everyone knows about that because they are talking about newspapers and the media, etc. Having said that, don't believe that bioplastics are able to sort out all these problems, because they are not able to replace plastics completely, and also so far they have an environmental impact as well, which we were discussing last time. We are going to show some more details into now, because plastics, this kind of plastic, petroplastics, are out of the food system. They enter the food system as in the role of packaging, but they are out of the food system. Bioplastics, the conventional bioplastics, so the one produced by polysaccharides, like starch, etc., they are inside the food production system, and which means that in some cases there is competition. You may remember the so-called cash crops, to make cash rather than to provide food. And bioplastics may be a part of that big question, because if I plant corn in order to make starch and make bioplastic instead that making food to be eaten, that might represent a problem, more a social problem than a environmental problem. Anyway, it's a problem. Okay, as I was saying, polymers, which constitute plastics, they are not synonyms, polymers and plastics, because in plastics there are polymers, which is the main bit, the main actor, and then there are some additives. Polymers may be thermally recycled provided they melt. They soften when. There are plastics which don't melt, don't even soften. They harden when heated, and they degrade in the long run. Thermosetting, like epoxy, some polyesters, phenols, they are resins. We call them as resin. They only partially enter the food system. For example, we may have they may enter it in a indirect way, because, for example, in a number of kitchen we have some furniture when we put food on, which is made of phenol containing plastics. So there might be some relation with food as well. The main question, though, is that the thermosetting cannot be thermally recycled, as it is the case for rubber. Vulcanized rubber, the rubber from tires, from car tires, cannot be thermally recycled. It can be, though, mechanically recycled. I can grind it and put it in something else. The new trend is putting it into asphalt, where it works. Well, in fact, it works quite well. Okay, there are some chemical reasons why thermosetting are like that, because they have cross links. They have this kind of network which is very stiff, and it is good that there are thermosetting. Don't mistake me, please, but it's good that we have thermosetting because we process them at ambient temperature. Most glues, most adhesives are processed at ambient temperature. The adhesive we in homework in DIY are normally thermosets, like acrylate, like epoxies and so on. They bond at room temperature. Okay, having said that, what was the aim for bioplastics is replacing thermoplastics. Most bioplastics are thermoplastics, although there is the possibility to produce also thermosets with some kind of agricultural even production or even waste, like some kind of vegetable oils. You can produce thermosetting resins. It's always a kind of bio-based material. You can produce thermosetting resins not using chemicals, industrial chemicals, but agricultural products like vegetable oils, like rapeseed or castor oil, which are two types of oil which have a limited interest for the food industry. Although they have an interest that comes and goes, like rapeseed had a period of very popularity in the 60s and 70s. And then it disappeared because of the presence of some acids which were toxic. Then the acids were removed from oil, this kind of oil, and now it's less acid and it's able to be used as an acid into food industry. Okay, so what happens with thermosetting? Are we obliged not to recycle them, just mechanical recycling? Well, there is some research. For completeness, I need to say that there is some research. There are works on phenols, which, because they don't but if processed at supercritical temperature, so you may remember that supercritical temperature means that they are not able to liquefy anymore. If we process them at supercritical temperature, we are able, in reality, phenols so processed with supercritical methanol, we are able to, in an atmosphere of supercritical methanol, we are able to transform them to carbon. Just carbon to make active carbons, electrodes, and so on. This is a research, more a research consideration than an operational consideration. But there is research in trying to dissolve or to recycle chemically, especially chemically, because more than thermally, because they really don't melt. But in chemical terms, you may add something to dissolve them, or you may process them at temperatures so high that they don't degrade anymore and they are able to depolymerize. You are able to break the crosslinks. Like in the case of phenol. Phenol is still very present in many resins, many resins, because it was introduced in the 30s. It's a nasty product in chemical terms. Phenol is really nasty, but gives resins which are very similar to wood as raw properties, and so it's unlikely to disappear. Okay, we come back with about what we were saying last time. Last time, you remember we had this problem with boys, and that's why I put some of the slides we were talking about last time, and particularly the two examples, the comparative production of plastic and paper bags. You may know that before plastic was introduced heavily, before thermoplastics were introduced heavily, which means in the 50s or so, when I am saying plastic, I'm saying plastics for bags, so low density polyethylene and then polypropylene. We may consider that they replaced paper bags. The problem, even if you don't know anything and you just look at this slide, you may consider that the processing is much more complicated. Much more complicated than that it was the case for paper bags. Paper bags means pulp production from a tree, or even from more recently from recycled cellulose. Then you produce paper, and basically you need a mold, and you make flat sheets of paper. You print, and then you shape paper bags by cutting them, or normally by cutting them, and by enclosing their shape with some kind of glue, which might be obtained from cellulose pulp as well. But anyway, plastic bags are much more complicated. A number of steps in the processes, a number of steps which involve starting from oil. So we need a cracking process. Cracking process means that we produce the hydrocarbon we need, for example, ethylene to produce polyethylene. Then we polymerize, then we produce the polyethylene. Then we need to add something else. There are a number of additives, and then you need to process. So we need to extrude and to spin. So we need to extrude in order to make the longer shape, the elongated shape, and then we need to spin to get to the production of the real bag. Spin gives you the possibility to make that not only elongated, but also to have the geometry to make it back in just one piece with no glue and so on. So you may understand why the production of plastic bags compared to paper bags looked so promising, because there was a reduction of price, just one piece. Well, of course, the process is complicated, but it can be managed, especially if the cost of oil is not that high. Okay, so extrusion and spinning. And this is extrusion. Extrusion means that you put the granules of pellets of plastic, which means polymers, which means of additives. There are always ceramics, some kind of ceramics like talc, calcium carbonate, and so on. You have this kind of screw, rotating screw, with heaters, because you need to get to the melting temperature. Then you can make, well, extrusion is not just good for sheet and films. You can make structural parts, you can make tubes and pipes. The important characteristic is that extrusion gives you a constant thickness part, which is important in the case of bags. It's very important to have a constant thickness, which is much more difficult for an exactly exact thickness of the structure of the bag in our case. So you can have some melt spinning for the production, for example, of continuous filaments. You can make filaments, you can make even fibers. You can make some calendering to make sheets. So you may have different processes. A process which is typical for the production of films from which you can make some bags. It's the production of the blown film process. Basically, it's important because you can extrude these plastic films into the shape of a bag. Okay, this is important, and this is important because it allows very high levels of production, very high volumes of production, so you can make many bags, many bags. That's very important. Okay, so we could consider that some of these processes are possible also with bioplastics, so the process doesn't change. The important thing is that if we want to replace plastic bags with bioplastic bags, the process should about stay the same. Some modifications, of course, for example, the heaters wouldn't work exactly the same temperature. The thickness wouldn't be exactly the same, especially if we want to make the plastic bags compostable. But in general terms, the process is closer than the two materials are. So the process used stays about quite close, although the two materials used are completely different. In one case, it's an oil-based one. In another case, it's a polysaccharide-based one. Okay. Then the other question is concentrating on an extrusion process really for creating plastic bags. Here again, we have the resin. We put in the resin with all resin means that we don't just have polyethylene. We just have all the additives. The additives are shown below. Some of these are not present in bags. This is said for completeness. We don't put usually glass fiber and carbon fibers in bags for the supermarket for food packaging. Although we do that, for example, in a number of composite materials which are used in industries and so on. But of course, we use functional additives, so additives which have a precise function. Each one has got a precise function. So we have plasticizers that allow better, usually these are alcohols which allow better to plasticize the material. Slip agent, curing agents. Curing agent means that they are able to control the process of solidification and then of cooling down. And we can have some fillers which are not only intended to make to increase the weight of the material, but they are also intended to make the processing easier, to make the plastic more suitable, more uniform. Mica, talc, calcium carbonate they are used a lot, in particular clay as well, because they have the limited cost and they work quite well. You may say that in most plastic materials, in most even kind of jelly materials like toothpaste and so on, you find calcium carbonate. Okay, so you extrude, you have this circular die, which is basically a mold, you extrude it, and then it passes through these rollers, your film, which is going up, is passing through this roller, and then you have this kind of roll of film. You have this film, which is then cut, and with some kind of melting, with some kind of local melting, you put together in just one piece in a bag. Okay, this is the general scheme of what we are saying. We are not studying anyway chemical processes for plastic production, so it's just giving some hints of how it works. Especially of the fact that any part of this process involves some environmental impact and the consumption of some energy if you have to go up in temperature, and then some other operations, some maintenance cost. As always, there is a capital cost, I buy that. Then there is a maintenance cost. I need to operate this system, I need to spend some more money, for example, to clean it, etc. And especially when food is involved, it becomes very important. Okay, then of course there are some other additives like colorants, well, but it is quite easy to understand that there are some pigments and so on. Now, it is interesting to say this because in bioplastics there is also the idea to introduce some agricultural colorants, some food colorants, because the characteristic is that in most cases in plastic bags, it's not always the case that food colorants were used. For example, soluble azo colorant, many of these are not certified for food use. I mean, I can use them into food bags, but provided they don't leach into food. So I need to apply in a suitable way, not to allow that, but I can not put them into food. Instead, there are some colorants for food, the ones which are indicated from the code, with the codes from E100 to E200, which are suitable to be put into food, into, say, liquor, into sweet and confectionery and many other things. Okay, having said that, we need to go out from the idea that everything works because is there only polylactic acid? That's the big question. Well, no, there isn't just polylactic acid. There are also other kind of bioplastic. For example, a good competitor of polylactic acid is polyhydroxyalkanoate. Polyhydroxyalkanoate is so-called bacterial plastics. Is the plastic that can be produced from bacteria, which basically transform cellulose and make plastics. This is not that strange because if you consider that wine becomes vinegar after a while by the action of bacteria, and we are able to control that process to the production of vinegar, as many, I open a parenthesis, as many food processes, this happened by mistake in the first place. Because if you leave wine for a while, it might become vinegar by mistake. After that, the process was industrialized many, many years ago, possibly 2000 years ago. We were already producing vinegar, but this is disconnects with what I am saying, that we could exploit what bacteria are doing on their own to produce plastics. And this works. The costs are high. To replace even polylactic acid, the costs are high. But this has an interest because this doesn't involve really any food producing system, but this might be done also with waste. This might be done from waste. We could transform cellulose waste, and we have lots of cellulose waste around, into some kind of bioplastics, and PHA is the candidate, the suitable candidate. What I can say also is that we have done an enzyme which is able to retransform and to degrade that plastics and to make it compostable at the end of life. So we may have a degradation with microbes and then a degradation with enzymes at the end of life. So this is a good perspective. The question is that the system is much more complicated than you consider. You need to avoid the interaction with food. So you need to avoid to produce bioplastic directly from food. It would be better to produce it from biomass. Biomass is it's a larger system than food. Food is much more concentrated. Food is just what you can eat. Biomass is anything that has an interaction with nature. So you may have a plant which is toxic. You may and you may consider it is part of biomass anyway, but not part of it. So this is one question. Another question is that you have alternatives. It's not just bioplastics. You may consider that you can produce biofuel, bioplastic, and bioenergy, in reality, biopower. The problem is that you may have fine particles, fumes, and so on. And you may have waste. You may have waste which is biodegradable but possibly not compostable, and which might represent a problem. I do a simple example. When you prune the trees, when you cut the trees, you may have some leaves and some branches which are not very good to make fire, to burn, but anyway you will have ashes then. They are not compostable at all. If you imagine this is the time for pruning olive trees, the virus allows us. But olive trees, olive branches are not very good for fire, and they are not compostable. They are biodegradable in a long time, but meanwhile, we may consider them as waste, so we may consider that we could do something with this. Bioplastics is an option. Then we have another question, which is the use of fertilizers. The use of fertilizers, it's critical because we need fertilizers, and with monocultures, like it is the case for corn, we use more and more fertilizers because, as I was saying possibly last time, if you heard my voice, but corn lives as a monoculture. Monoculture has no enemy. No enemy means that it becomes weaker. The plant becomes weaker and needs more and more fertilizers and pesticides and so on. Because if no enemies around means also that if an enemy arrives, it might be crucial to get rid of it by pesticides. Then it weakens, it becomes less productive. The yield becomes lower, and I mean more fertilizers. which are chemicals, toxic chemicals, and so on. So there is a big question whether pesticide-free bioplastics might become free. Because in principle, I started from a material from cornstarch, which was produced by making large use of fertilizers and pesticides. What is the view of Europe? The view of the European Union is to try to go for compostable plastics. In other countries, so to replace basically the oil-based plastic, the petroplastic, with compostable plastics. In other places, in other countries, like the US, like India, they have a different attitude. They have a different attitude because they still think that it would be better to degrade these plastics into landfill. Why so? It's not because they are bad and they are good. It's more complex than that. We have different visions because they want to have a high quality plastics. Because you may have seen that the old polyethylene bags were of much better quality than polylactic acid bags because they are thicker in the first place, but also because they are stronger. They have a much higher shear resistance. They don't get cut easily. Low density polyethylene. So in practice, what was the idea? We keep the old plastics. We don't care to produce them like with ethanol, like other countries were doing, like Brazil, for example. We have no problem, no shortage of oil. We produce them still from oil. We keep our old plastic bags with our old thickness, and we can reuse them a number of times. Consider that if plastics is weaker, you are not able to reuse it. Instead, with low density polyethylene, you can reuse it many times because they tend to be clean, more or less, plus they are stronger. Don't mistake me, please. I am not saying that I would like to come back to the low density polyethylene, but I need to show that this exists. What they do in practice, they add some biopolymer based additives, which means that once you put them into the soil, you grind them into the soil, it decomposes in microplastics. And this is the vision they have. They are called oxo-degradable bags. Basically, if there is a lot of oxygen and a lot of bacteria, they tend to decompose. We are able even to decompose them into oxygen flows and then rebuild the plastics. And they make them melt easily and recompose it. But in the first place, they last more. Please remember that the first sustainability is duration. Of course, the European Union doesn't agree with this perspective, and I can understand why, because then you may find out that if you don't control landfilling, you may find out that they get into water and fragments get into the sea and interact with plankton, then with fish, etc. And so we get them back into our food. We need to come out from the dream. We eat some plastics. We eat some limited amount of plastics. So it's not true that we eat zero plastics, but we need to limit it to the minimum. We eat some plastics because there are some food, including fish, which contain some minimal amount of plastics, and they re-enter the chain, the food chain. And also there are some, thinking of toothpaste, for example. It's quite easily that some minimal amounts of toothpaste go down your your body, and in the end, you end up eating some plastics, because also some polymers which are not that far from the ones we are using in plastic bags and so on. So we need to be clear about that. Anyway, these are two different perspectives, and they collide in each other. The Europe has some countries in Europe have been very aggressive on that, like the Netherlands. The Netherlands have completely banned this kind of oxo-degradable bags. So the old polyethylene, low-density polyethylene bags with some added components which make it degrade. But also, this can be done with any plastics in principle. And some attempts have been done to use it also with resins and so on. Even there are some proposals to use it with thermosetting plastics and so on. So it's, I'm not sure this will disappear in the long run. Okay, then the other example was a substitution, as I've shown already last time, that we have PLA with to substitute PET. We have some examples already, also in Italy. Here, this is a study which is, as I was saying, was about suggestive. Don't take for sure the numbers. The numbers may always change. It's important the concept. They try to group the different impact with different in two different categories, into three categories: the ecosystem quality, the resources, and the human health. And you can give more weight to one of the three the possibilities. You can give more importance to the ecosystem quality, or to the resources, or to human health. It depends. If you are, of course, if you are in a urban context, then human health, since you have many people around, becomes of paramount importance. If there is limited people into there, or if you are, or if you are in a context where just in a depopulated context, you may consider that human health is not less important, but has less weight. You have to protect the environment in the first place. Let's say if you are in a natural park, of course you protect the environment before humans, because there are no humans around. In other cases, if you are in a context where it's equally depopulated, but the environment is not particularly nice, but it's possibly a landfilling site, we are going to or a quarry, an old quarry, we want to we want to bring back to its original conditions, or we want to establish possibly some vegetable croppings and so on. Then resources become more important. That we don't consume many resources to produce the polylactic acid bottles with respect to the PET ones. It's, for example, if you have a factory which is placed in a place where we have lots of resources, but again, the depopulated place and so on. So this is much more complex than I was saying, because it's always a model. So it has betrays the reality in some ways, but this gives you an idea of what is more important in the place. Because in practice, this might seem quite unpolitical, but in practice, what happens is that people shift from the polyethylene terephthalate to the polylactic acid, because, for example, they don't have much oil in the first place. So they might have lots of agricultural crops instead, and they may consider, why not shifting from polyethylene terephthalate to polylactic acid. That might be one of the consideration. That's the same case as I was saying for oxidizable polymers. In the US, they have lots of, they have no problem with shortage of being provided with oil, of oil supply, and therefore they tend to preserve the plastics rather than the PLA, which would involve other problems because possibly they use corn for other purposes of food, etc., or fuel, for agrofuel, etc. Okay, PLA can be composted. Now, with the European legislation has concentrated on composting PLA. This is not the only option. We might consider also to recycle it, or to landfill it, or to incinerate it. This is a comparison between PLA, PET, and polystyrene. Because polystyrene, you can produce bottles in polystyrene, which are not the collapsible bottles we know, but we may consider also some other more vitreous bottles in polystyrene and more brittle as well. But anyway, they are not in Italy, for example, they are not allowed for the production or for the use with water, not at least the disposable ones. But anyway, these are the three competitors. You may have different disposal scenarios, and you may consider that. Please consider one thing, that you may not always have, in some cases, 100% compostable. You may consider that some of these can be also recycled instead of composted, and or incinerated. In this case, compostability was not considered. They consider three scenarios, like recycling. Of course, it could be recycled polylactic acid. You need to make it thicker. Of course, it's more expensive. You can put more ceramics, for example, as fillers, and it's thicker and it's not compostable. It can be recycled because it's stronger. For example, PLA, which you use in 3D printing, is not compostable, but can be recycled because it's much stronger. It has some additives like clay, and well, it has good properties, and it can be recycled. Of course, also thermal recycling, not just mechanical recycling. Okay, so you may have different scenarios, and you may have different impacts in greenhouse effect terms, so carbon dioxide emissions and energy consumption in megajoules. Okay, these are some data that show you just also that you can compare different scenarios. Okay, we are almost at the end. Another possibility was polyhydroxybutyrate. It's another competitor with PLA and PHA. I have already shown this last time. I don't go into much details, but of course there are different stages, and you need to consider. From corn starch, you can produce also the polyhydroxybutyrate, which has higher costs, but in reality it can produce. You can have a fermentation with bacteria at the end of life, or you can have an energy recovery process. So in practice, you can burn it. You can burn it. It's difficult to recycle it. It probably doesn't have the strength to be recycled. But this might always come. It's important to be clear that there are different sources of impact. You can have a fermentation from bacteria. You can recover. Possibly you can decompose it with bacteria. It's not completely compostable. Therefore, we can burn it after it has been decomposed. It becomes a biomass which we can burn, which we can compost if possible, which is not always the case with polyhydroxybutyrate. what I would like to be clear with this course is that we need to be clear about the method and analyzing the different factors and the different actors involved in the process. You may see that the reality is not simple because, for example, in polyhydroxybutyrate, I may have fertilizers which are not the same as I was using in polylactic acid, even if I always want to produce cornstarch, but possibly I may use different fertilizers because I might need a cornstarch of different quality, of different mechanical and technological characteristics, and so on. Because then I need to process the material. Don't forget I need to process the material, and therefore cornstarch might be of different quality, etc. Chemicals, fuel, etc. And other chemicals involved in all the process, which are possibly involved in the production of plastics. I may need to plasticize glycerol. I may need glycerol to produce plastic. Glycerol is not involved into the cropping, but it is involved in the production of plastic. So it's a chemical anyway, and has its own. Okay, so what happens? In the end, I could, it's always a waste, not using waste, if you allow me that kind of sentence. Because I could, instead of planting corn, I could take the part of polysaccharide substances which are present in corn, for example, in leaves, which contain a lot of cellulose, etc. I can make starch out of this, and I could have a biorefinery. Now, a biorefinery, for example, I get agro-food waste, even a general waste. Don't go into details about the process, but for example, here we had brewery spent grains. There is one important concept which is true for, say, 100% of the cases. That if you make a lot of money, if you have added value from your cultivation, for example, you make beer, you make beers. And beer have a lot of added value because you pay it a lot for comparing with the value of the grains and of the process. That means that waste becomes a problem. If the added value is high, waste becomes a problem. If waste becomes a problem, I may consider, for example, to use it for making bioplastics. Here we have waste from brewery spent grains, and I can produce ethanol, which is used in a lot of chemical processes, including making other liqueur or beer or wine and so on. Then I have glucose, and I can make ethanol. I can make xylitol, which is used a lot as a plasticizer. The main use of xylitol is in chewing gums, but it's used a lot to plasticize and to make more rubbery lots of food items also, because it cannot be digested, but in small amounts it can be eaten. And also it's used also in some cosmetics and similar. And always as a plasticizer to make it more jelly and more rubbery between gel and the rubber. Okay, anyway, therefore we can produce polydroxybutyrate also from waste and in a kind of system which is called a biorefinery. The advantage is that it will cost less, especially if it is combined with other items, other chemical items, which have a considerable added value in themselves, like ethanol and xylitol. This brings down the cost of polyhydroxybutyrate. The advantage is that I could consider it as a bioplastic, as an alternative, which is at the moment the king of the market of bioplastic, but this may not last for long. Okay, we stop here. We see you on Wednesday. We'll carry on this question, and we'll concentrate on composting because we have talked a lot in general terms about composting, but we need to go deeper into what is the environmental impact of composting, because there is one, and we would like to understand also if there are alternative ways of composting to reduce the environmental impact of the process and possibly to produce a better compost, because the main complaint of people working in agriculture or farmers is that compost produced with bioplastics is not of the same quality of what we can produce from cattle, from animal activities. Therefore, well, there is a big concern about that, because if the product is not that good, then in the end, and our introduction bioplastics would be harmed from the beginning. Okay, as always, please feel free to write me if you have any doubts. I'll put them into the e-learning platform, this recording, and also possibly on YouTube, but please consider more the e-learning platform at first. You'll find also these slides into my web page in a few hours' time. And this is number 3. And okay, please feel free, as I was saying, to contact me. Have a good day, and see you on Wednesday.